refraction through prism, it means rays of light made to pass through the prism, and then the light ray will be refracted, and we will study the relationship among the angle of incidence, angle of emergence and refractive index of the prism. So this is a prism, this is called triangular prism. Okay, in this triangular prism you name this portion as ABC, three-dimensional solid, A dashed, B dashed, C, opposite faces a triangle. This ABC, if we take here and keep it this manner, then this can be referred as the principal section of the prism. This is the principal section, ABC. Then let us make this one inclined. Okay, you can take this portion also as you like, ABC, ABC, A dashed, B dashed, C dashed. Okay, but I prefer to get this manual diagram, or this way I am doing it with you, taking prismatic view like this. Like this. So ABC, if it is here, triangular prism I am telling you again and again, so that it will help you to visualize the diagram, to visualize the process. If I have taken a ray of light this manner, it will suffer refraction at this face, isn't it? It will go inside this manner up to this, then it will suffer refraction here inside, and then it will emerge like this. But we cannot draw this diagram always. I will be taking this principal section. This is called, in your mind it will play like this, that this is the principal section we are considering, but actually what is happening there? Light suffering a refraction this manner, goes this way, then refracted this way. Now this light, this will refer as incident ray, this is emergent ray, and this one is the refracted ray. Okay, we go back to the prism case here. This ABC is known as principal section, BC, C dashed, B dashed, this is the base of the prism. Okay, and AB, B dashed, A dashed, AB, B dashed, A dashed, and AC, C dashed, A dashed, these are known as refracting faces of the prism. Clear? So you understand? Two refracting faces are there, and this portion, this edge where two refracting surfaces meet, that is called edge of the prism. Okay? This portion is called edge of the prism. This is edge. Clear? Hope you understand. A prism, three-dimensional shape, which on base, what are refracting faces of the prism, that I have explained. Now this prism is a three-dimensional object. It has the property to refract this light ray. So definitely it has a fixed value of mu. That is called refractive index. This prism, brilliance of diamond you have done. Does it have any brilliance here? No variable refractive index. This refractive index is fixed. We will not compare it with the diamond. It is just a prism. Prismatic shape is there. Same refractive index, not variable refractive index. For special purpose we can do that, but here it has refractive index same. Now, when there is incident ray, refracted ray, emergent ray, there must be angle of incidence also. But I will not draw this diagram again and again. Let me finish that part only. How normal is there? Normal is perpendicular to this surface. You agree? You should agree. So if this is the normal, then angle of incidence I1 lies here, and this is your R1. Again, you draw normal here, normal to this surface. This angle is R2 and this one is I2. This one I2 and this angle, this is the normal, no? So this angle is R2. Clear? And very important thing you should remember, if mu greater than 1, then the emergent ray bends towards the face of the prism. Face of the prism is AC, C dash, T dash. It will bend to, sorry, I am wrong. If mu less than 1, it will happen. It will not go towards base. If mu less than 1, then emergent ray bends towards the face of the prism. But if mu less than 1, then if mu is greater than 1, this is the case, less than 1 we have already considered. If mu greater than 1, then the emergent ray bends towards the base of the prism. Normally this case arises. Mu refractive index greater than 1. It is made of glass. Whatever liquid or glass you consider, it has refractive index always greater than 1, so it will bend towards the base. Okay? So hope you have understood which one is I1, which one R1, R2 and I2. We will be referring I1 as angle of incidence, I2 as the angle of emergence. or not to inside, we are not very much interested about that, except that mathematical calculation. Now I have to find deviation produced by the prism. How much deviation is produced by the prism? Let me explain. Deviation produced by the prism. For that purpose, what we have to do, we have to produce this ray in forward direction, this ray in backward direction, then this angle. Let me do it in different diagram. The deviation produced by a prism. Deviation produced by a prism. As I told you earlier, I will be taking the cross section of the prism only. Always I will take the cross section. Whole prism I must not carry. This is the cross section of the prism. ABC is the cross section. Take the incident ray here. What will happen to this ray? It will suffer refraction. Then it will suffer further refraction at the second phase. Clear? We have already drawn normal, all those things. This is the normal drawn at this point. This is the normal drawn at this point. O1 is the angle, is the point of incidence. O1, here O2 is the point of incidence. Already I have mentioned which one is I1, R1, R2 and I2. If you consider this vertex angle, this is called angle of prism. Angle of prism or angle of refraction of the prism. Okay, that will always consider angle A. So angle A stands for what? It stands for the angle of prism. Clear? Now what we'll do, we'll find the angle between these two directions. Which two direction? I am just producing it forward direction. It is supposed to go this manner, isn't it? But finally it goes this way. You produce it backward. So this emergent ray produced backward and incident ray produced forward. The angle between these two directions is called angle of deviation. Let us define. Angle of deviation will be taking as delta. Angle between, this is incident ray, angle between the incident ray and this is emergent ray. Angle between the incident ray produced forward and the emergent ray produced backward. So in this diagram, which one going to be that angle? This is the angle. This is the angle. This angle is called angle of deviation. Clear? Our problem is to get that angle of deviation here. This angle delta we need to find. Okay? Just a minute. I hope I will be able to take the whole diagram together. Yes. Making it a bit larger for you. I think it is visible for you. Which one? Angle of incidence, angle of refraction, and what is angle of deviation? You can see properly. Clear? Delta is the angle of deviation. Okay? We are going to find the value of delta in terms of I1, I2, R1 and R2. Here delta is equal to this angle. It is the sum of two interior opposite angles, this one and this one. But this one is what? Total angle I1, this is R1. So this part will be I1 minus R1. Am I correct? O1, O2 and this meeting point, if you take L, so in triangle O1, O2, L is their meeting point. Incident ray produced forward and refracted ray, emergent ray produced backward. In triangle O1, O2, L, delta is the exterior angle. This is nothing but angle L O1, O2 plus angle L O2, O1. L O1, O2 is what? This one I1 means total angle opposite is I1. So this will be I1 minus R1, I2 minus R2. So this thing going to be I1 plus I2 minus R1 plus R2. Clear? Now what is R1 plus R2? You just produce this one again, just slightly. I am considering these two normals meet at M. So in A01, M02, in this quadrilateral, this is 90, this is 90, this total angle 90, no? You can see this total angle also 90. So 90, 90. So sum of this and R2 also must be 90, 90, 180. Their sum must be what? A plus this angle, this one. This is R1. This is R2. This is 180 minus R1 plus R2. A plus 180 minus R1 plus R2 should be 180 degree. Clear? Why 180 minus R1 plus R2? Because in this triangle R1, R2, in triangle O1, M, O2, R1 plus R2 plus O1 MO2 equal to 180 degree. So O1 MO2 will be clear? 180 minus R1 plus R2. So this relation is valid. From here what do you get? A equal to R1 plus R2. I explain once more. This angle, oh my God, this angle A, apex angle A and this one O1 M O2, this has to be 180 degree. Why? Because AO1M 90, AO2M is also 90. So sum of this and this has to be 180 degree. So A plus A, this angle A plus this angle has to be 180 degree, because this is 90, this is 90. From there we get A equal to this thing. Now what about delta? What about delta? This delta we are going to write. We got A equal to R1 plus R2. This you take 1 and this one 2. So from these two relations, from this one and this one, this implies that delta equal to I1 plus I2 minus A. Number 3. I1, I2 angle of incidence and emergence, that minus A will give you angle of deviation. Clear? Done? Delta equal to I1 plus I2 minus A. Now, what we are going to do, we are going to find the delta versus I1 graph. But this time practical experiment. I am not doing any mathematical help here. Just some experiment done by others or with us in our student life that I am going to share with you. How delta varies with I1. What is I1? I1 is this angle. Delta, incident ray and emergent ray produced backward, angle between them is delta. If you plot delta versus I1 graph, the graph going to be like this. This is your I1 and this is delta. Experimentally, if we plot the graph will take this shape. But it's a question for your board exam. How do you answer this? You have to be little bit good in English writing the answer of this part. So it is experimentally observed or experimental observation. Okay? So to plot the graph, I'll keep this thing in mind. This is my incident ray HO. Keeping HO fixed, HO fixed, this HO, you understand which one HO? This is the incident ray HO. Keeping HO fixed, if I1 changes, then delta changes as above, as in figure. So what is happening there? If somebody asked you to study this, you will say that as I1 increases, the value of delta decreases, and then it attains minimum value at some point, I1, and then its value goes on increasing. This is our observation from the graph. Clear? So initially delta decreases as I1 increases, it attains the minimum most value, and then its value again increases with I1. And please remember that this is a direct experimental observation. Direct experimental observation. You cannot put forward any reason that your experiment was wrong, you have done with different wavelength of light. No, this will always happen. And this minimum deviation for which you are getting, for that angle of incidence you are getting, it has unique value for a particular prism. Okay, so that also done from experimental observation. Also for a unique position of the prism, it is possible. This implies that is for only one angle of incidence, delta is minimum. Clear? Only one angle of incidence, delta is minimum. Now for that minimum deviation, we are going to prove that I1 must be equal to I2. Let us prove it. So to prove that, once more I tell you, I just remind you why have I got this graph. What I did there, in this diagram we kept H1 fixed, then setting the prism at different orientations. Then you get different value of I1, that we have plotted here, and experimentally you have observed that for unique position of the prism, minimum deviation is possible. For a particular prism, for only one angle of incidence, deviation is minimum. Please don't forget this. We are going to find the condition for minimum deviation now. Condition for minimum deviation. For minimum deviation, it can be proved that I1 equal to I2. Let us prove it. Answer. Draw the same diagram which you have done earlier, showing the angle of deviation clearly. Take one incident ray. This is refracted ray, and this one emergent ray. Clear? Incident, refracted. What you will do? This will produce forward. This you will produce backward. This is angle of deviation. I told you clearly in the previous diagram. This is the point of incidence on this refracting surface, point of incidence. Refracting surface, that concept will be there in your mind always, what I told you in the beginning. So here, this is the scenario. Clear? This is the incident ray, HO1 incident ray, and considering refraction at O1 and O2 then. So angle of incidence is well defined term. This, if I draw it, it's okay, fine. We are drawing that also. Yeah, this is I1, you remember, this is R1, this is I2, this one R2. So to prove this, I'll give you the logical proof. There is a proof, very interesting proof by using calculus. You might be very much interested about that, but I'm thinking for all of you, without much mathematics, how by using logic of physics we can get it. So taking HO1 as incident ray, we have delta equal to I1 plus I2 minus A as shown in figure. Now what I am going to do? I am going to take a mirror. I am going to take a mirror in front of this ray, normal to it. This is a mirror. To reverse the direction, light ray will reverse the direction in forward direction by principle of reversibility of light. So we'll write that now if the emergent ray is reversed by using a mirror as shown in figure. If the emergent ray is reversed using a mirror as shown in figure, then light travels the same path in opposite direction. Clear? This is by principle of reversibility of light. It will travel the same path in opposite direction. Clear? It will travel the same path in opposite direction. We are reversing. So it will go opposite manner as shown in the diagram. But this time, here also, deviation will be what? By the previous concept, delta dashed will be I2 first, I1 minus A. Why I2 first? Because here I1 is the angle of incidence, that's why it comes first. Here I2 will come first, because light going this way. Clear? We got delta dashed also, same expression, the same way we will get only, no? That proof we need not give. We are all in class 12, isn't it? So, what do you observe from 1 and 2? From 1 and 2, we see that delta equal to delta dashed. Isn't it? We see delta equal to delta dashed. But both are minimum deviation. Same prism light you are sending this way or this way, it doesn't matter. So what you have observed, logically when you explain you have to write. Therefore, for two different angles of incidence, I1 and I2, we get same minimum deviation. We get same minimum deviation. but it is a contradiction of direct experimental observation. What is that? That only for one angle of incidence you will get minimum deviation. So for I1, I2 it is not possible. So only one possibility is there, that I1 must be equal to I2. Otherwise deviation, otherwise for two different angles you are getting same minimum deviation. It is contrary to the principle of direct observation. It is not possible. Clear? So I1 must be equal to I2. Therefore, I1 not equal to I2 is not true. Initially we have assumed that. So I1 must be equal to I2. Clear? Now, if you see the diagram, you have done I1 equal to I2. I am going to state something different now, that if you say I1 equal to I2, then what about R1, R2? In figure, mu equal to sin I1 by sin R1. Also mu equal to sin I2 by sin R2. Alright? So these two are equal. Sin I1 by sin R1 equal to sin I2 by sin R2. But you got I1 equal to I2. So cancel this fact. This implies sin R1 equal to sin R2 or R1 equal to R2. So for minimum deviation, I1 equal to I2 and R1 equal to R2. Direct observation will tell you I1 equal to that minimum deviation position is unique. Then by performing experiment, that theoretical experiment, you have proved that I1 should be equal to I2. So I1 equal to I2. Now all this discussion when you are doing, it has some very good application. That I1 equal to I2, we have proved R1 also equal to R2. So what is delta M now? Now delta M equal to I1 plus I2 minus A. A means what? R1 plus R2 or 2R1. So you write 2I1 because I2 equal to I1, 2R1. So delta M by 2, therefore I1 equal to what? Delta M by 2 plus R1. R1 is what? A by 2. So delta M plus A by 2. This is for I1. Clear? Delta M plus A divided by 2. Now does it, I told you it will help some other way also, that I1 R1 you got. Now mu equal to what? Sin I1 by sin R1. Sin I1 how much? Sin I1 how much? A plus del m by 2. R1 is what? A by 2. So what have you got for minimum deviation? Mu equal to sine A plus del m by 2 by sine A by 2. This is proved, and this relation will help us to determine the value of mu of a prism, or if mu is known, delta m we can find easily. Clear? That's all about prism. That's all about prism. Problems are there definitely. Next day, next Friday, it will be on problem solving from geometrical optics, and we will be solving at least 20 graded sums in 2 sessions. 10 sums will be from reflection and basic refraction. We will categorize this way. And remaining 5 sums, no, we will do 5 from reflection, just graded sums, good sums. 10 from where? 10 from lenses and spherical refracting surfaces, and 5 from prisms. Get ready for that. 5 from reflection. We have done simple problems. We'll do some graded sums, very important. So you need to revise mirrors, reflection. 10 sums from spherical refracting surface and lens, 5 from prism. Clear? See you again next week.